Cardiovascular disease is the leading global cause of death, driving interest in early diagnostic methods such as ECG, ultrasound, phonocardiograms, and photoplethysmography. But compared to others, PPG offers a few additional advantages. It can provide more information, is easy to acquire, does not require electrodes, and can be easily integrated into wearable devices. Despite these advantages, PPG is mostly limited to heart rate, SpO2, and heart rate variability monitoring due to limited understanding of the physiological factors influencing its waveform. Therefore, our goal is to identify which physiological factors cause changes in the PPG waveform by using a mathematical model of the cardiovascular system and PPG acquisition. Our project deliverables include characterization of the PPG signal, validating this characterization using simulated and real data, and extending the use of PPG by developing a blood pressure estimation model and an atrial fibrillation detection model. Our project focuses on enhancing PPG use through 5 areas: mathematical modeling, PPG characterization and validation, system identification, blood pressure estimation, and AFib detection. We modeled PPG waveforms by simulating arterial blood flow using partial differential equations based on Navier-Stokes and pressure area relationships, with aortic inflow at the inlet, conservation lows at bifurcations, and the Wien-Kessel model at the outlet. Using that model, we can obtain the flow rate and luminal area at the radial artery. These outputs are then used to simulate light propagation through the skin using the Beer-Lambert law. This allows us to generate simulated PPG signals. We characterized simulated PPG signals by weighting key cardiovascular parameters such as stroke volume, diameters of the arteries, and stiffness of the arteries, and analyzing how these changes affect defined PPG characteristics. This table shows how PPG characteristics change in response to different cardiovascular parameters. We validated the results by comparing them with actual data from patients with hypertension and diabetes, also taking into account the viscosity differences between males and females in our simulations. Let's move on to the system identification process. Flow rate waveforms have more detail than PPG signals. Our goal was to reconstruct flow rate using non-invasive PPG. We used synthesized flow rate PPG pairs with flow rate as input and PPG as output to estimate the system. A first-order transfer function gave the best results. We found gain has a quadratic relationship and the time constant a power-law relationship with fat layer thickness. We used the inverse model on unseen PPG signals to reconstruct flow rate. Results showed higher correlation and low error, confirming accurate reconstruction. Now let's move on to the atrial fibrillation detection. Atrial fibrillation, also known as AFib, is an irregular heart rhythm caused by disorganized atrial electrical activity, which is a strong risk factor for stroke. This is depicted in the PPG waveform through the irregular pulse rate and the pulse morphology changes. In our implemented algorithm, after a signal quality indexing through a feature-based support vector machine classification, the high-quality signals are then used for the AFib classification. With a range of features calculated, including interval-based, entropy-based, and morphology-based features, using a random forest, we classify the signals as AFib and non-AFib. Through this, we have been able to achieve comparable results to the different methods implemented in literature. Now, moving on to the pressure estimation. Many studies aim to predict blood pressure using PPG. We developed a machine learning model that uses characteristics from simulated PPGs for accurate BP prediction. Our model uses PPG segments from patients and healthy individuals. A custom pre-processing pipeline guided by simulated PPGs feeds an attention-based deep learning model to predict systolic and diastolic blood pressure. We extract PPG pulses from segments, filter out noisy signals using correlation with simulated PPGs, and retain the best 8 pulses, and compute key temporal features. The model has two self-attention layers for PPG and template signals, followed by cross-attention to learn interpulse relationships. A dense layer uses these outputs and temporal features to predict blood pressure. This compares our model results with existing literature, showing promising outcomes compared to state-of-the-art models while having a low computational cost. With this, we believe that PPG can be a prominent biosignal for diagnosing cardiovascular diseases in the future.